Hi, this is an example problem from Chapter 24 on the Doppler effect. Pause for a moment to read the question. So we have some emitted electromagnetic waves from hydrogen atoms. And when we observe these in the laboratory, we get a wavelength of 410 nanometers. So this is your unshifted wavelength. However, when we're looking at the same electromagnetic light emitted by hydrogen atoms that's coming from a distant galaxy and has traveled down to Earth, we're getting a different value here. This is your Doppler shifted wavelength. Now in part A it says, is the distant galaxy approaching the Milky Way or is it receding away from us? Well, let's go ahead and look. The shifted wavelength is longer, right? It's longer than the unshifted one. So let's go ahead and look real quick here. This is a little figure that shows us what happens to the wavelength when the object is moving towards or away from an observer. And you can see that from the observer on the right, the source, the star in the middle, it's moving away, and that's causing the wavelengths to get longer. They're spreading apart. Red is a longer wavelength than blue, so we call that a redshift. Whereas for the person on the left, it's moving towards them. The wavelengths are compressed. They get shorter. That's a blue shift because blue waves are shorter than red. But we can see for sure that we have an increase. The Doppler shift is a longer wavelength, therefore this is a red shift. Therefore the source is moving away from us in this problem. It's receding because the shifted wavelength is longer. And in part B, it asks us, use the Doppler shift formula for electromagnetic waves to determine the relative velocity of this distant galaxy. Well, let's look at the formula for that. So here's the formula that we want to use. Go ahead and copy this real quick. Alright, so there's all the information that we'd like to use here. Now notice that in the equation we have frequencies rather than wavelengths, so we're going to need to convert the wavelength to a frequency, and we'll use the good old formula, speed is equal to wavelength times frequency. We want to solve for the frequency knowing the wavelength, so that's going to be a formula, the frequency is equal to the speed of light divided by lambda. And now we're going to want to go ahead and use this same formula to calculate the frequency for the Doppler shifted and for the unshifted waves. Alright, so notice how we describe or we notate these things. So for the Doppler shifted frequency, we put a 0 by it right here. And for the source frequency or the natural frequency, this is a frequency when the source is not moving with respect to us, we call that S. So in this case we've got the Doppler shifted wavelength, which is equal to 430.5, so we've got 3 times 10 to the 8th meters per second divided by 430.5 times 10 to the minus 9th meters, nanometers, right? And for the shifted, sorry, that's not shifted, for lambda s, the source frequency, that's going to be, again, speed of light, 3 times 10 to the 8th meters per second, divided by, this is the laboratory line here, 410 nanometers. I'm going to go ahead and just fix this real quick since I don't want to get confused about this stuff. So this is the Doppler shifted wavelength. Shifted, it's longer. Now putting these values into the calculator, we get for the Doppler shifted frequency, it is 6.97 times 10 to the 14th, 1 over seconds. And for the natural frequency, it's 7.32 times 10 to the 14th. 1 over seconds, or hertz we can write. So we've got all information here that we need to be able to use this equation now. The last thing we need to do is pick the plus or minus sign. And it says we know that this is receding from part A, so we're going to do receding. That's the minus sign. So the equation that we want to use for part B is going to be this. F0 equals Fs 1 minus V relative divided by C. And we are trying to figure out the relative velocity of the distant galaxy, so we need to just do some algebra to solve for V relative here. So let's go ahead and do that. First of all, let's go ahead and multiply out the source frequency by both terms. And let's go ahead and move, we'll add the Fs over C to both sides, and we'll subtract the F0 from both sides. Finally, all we need to do is multiply by C over Fs on both sides. And we're going to get the equation for the relative velocity here. So, VREL is equal to C over Fs multiplied by Fs minus F0. That's going to be equal to, well, this is the easier way to write it, C times 1 minus F0 over Fs. Then we can simply take the ratio. So plugging in those values, speed of light, 3 times 10 to the 8th meters per second, multiplied by 1 minus F0, 6.97 times 10 to the 14th, 1 over seconds, divided by 7.32 times 10 to the 14th, 1 over seconds. Putting that into the calculator, we get a value 1.43 times 10 to the 7th meters per second. And so that's the relative velocity of that distant galaxy as it is receding, moving away from planet Earth. And this is really a example of what we know as Hubble's law, which tells us that all of the other distant galaxies are expanding away from our own galaxy in any direction we look. And the further the galaxy is, the faster it is moving away from us.